and moment is going in a clockwise direction. Okay, so this is the positive shear and positive bending moment assumption. Okay, so when this is the case, right, plus dimension of forces in the y direction at point C. So V at point C plus by 40 times 10 to the power 3 is equal to 0. So V at point C is equal to minus 40 times 10 to the power 3. Okay. And then we're going to take moments. Right. So we're going to take moment. Summation of moment in the x direction anywhere at 3.2. Okay, which is at this point. Or point C. Okay, we just call is equal to 0. Okay, so now the 40 times 10 to the power 3 is positive, multiplied by a distance of 0.8, plus or minus m as a function at point C is equal to, so m at point C is equal to 40 power 3 times by 0.8 is 32 times 10 to the power 3 Newton meter. Okay. Right. So I'm going to put minus 40. Okay. So at point C, this is minus 40 times 10 to the power 3. And then it is 32 times 10 to the power 3. Okay. And that is 3.2. Okay. Okay. Now, from point C to, okay, I'll show you the same point. Okay, let's say you don't want to do from right to left, you insist of doing from left to right. Okay, so we'll still do point C. Okay, but we're x equal to, or I'm going to write this down as alternate method, or more confusing. Where x is at point C, x is equal to 3.2 meters. So we are going to do analysis from left to right. Okay, let's say you did not want to learn right to left, you have to do left to right. You can, but I'll show you the consequences. Okay, so the consequences is as follow. So you have more points to consider now. Okay, so you know your distance over here. This is your 120 times 10 to the power 3. And then you have your equivalent load down here, which is equal to 50 times 10 to the power 3 multiplied by a distance of 3.2. So 50 power 3, that's like 3.2. So this is 160 times 10 to the power 3. And we know that this distance, right, this distance from here to here is 3.2 minus by 0.8, okay, 2.4. And the distance from here to here is equal to 3.2 divided by 2, which is equal to 1.6. Okay, so 1 is 2.4. And then we are doing left to right analysis, right? So positive shear is coming down here. So V at point C. And then moment at point C. So the answer will be the same, but you have more things now, right? Down here, you only have one force down here, you have to consider like two forces and two distance. More components you have, easier to make mistakes. Okay, so you can do positive dimension for forces of y is equal to 0. Then from here, you will realize that you get 120 times 10 to the power 3 minus by 160 times 10 to the power 3. And then you have minus Vy or V at point C is equal to 0. So V at point C is equal to 120 power 3 minus 160 power 3 is equal to minus 40 times 10 to the power 3. Right? So now you take your moment exactly at point C is equal to 0. So you have going minus 120 times 10 to the power 3 multiplied by 2.4 plus by 160 times 10 to the power 3 multiplied by 1.6, right? Then plus by moment at point C, the whole thing is 0. So moment at point C is equal to minus 120 power 3 or 120 power 3 times by 2.4 minus by 160 power 3 times by 1.6 is equal to 32. So the values are exactly the same, okay? But if you do right to left, it'll be much quicker, okay? Especially when you have to form equations, okay? So the last equation that we're going to do, okay, the last equation that we're going to do is from point C to point D, right? And we're lucky we are doing from right to left, right? Right to left. It's so much more easier, okay? So we have 3.2 Z, and it's going to go to 4.0. Okay. So you only need to consider this part, right? So we know that the force down here, this is equal to what? 40 times 10 to the power 3. And the distance, okay, from here to here, this is your x, right? Sorry, your z. And the distance from here to here is 4.0. So 0.8. Yeah, 4 minus z. Not z minus 4 because it has to be a positive value, right? So positive shear is going up now. V as a function of z, and then moment. Okay. So finally, right, we can do our stuff. So positive, right? So you will have 40 times 10 to the power 3 plus by v as a function of z is equal to 0. So v as a function of z is equal to minus 40 times 10 to the power 3. Okay. And this is a function, right? Because it's a range, but it's a constant value. And then dimension of moment z, sorry, x as a function of z. So we're going to do this point now, right? So it's going clockwise. So 40 times 10 to the power 3, right? 4 minus z. Okay. And then we're going to have what? We're going to have, it's going clockwise, minus m as a function of z is equal to 0. So m as a function of z is equal to wait, let me anti-clockwise is positive. Yep, it's correct. So it's equal to minus 40 times 10 to the power 3 Z plus 40 power 3 times 4 is equal to 40 is equal to 160. Okay. So how do you know that this moment is correct, right? So when you substitute Z is equal to 4, the whole equation has to be equal to 0. So when you substitute Z is equal to 4, right, which is exactly at point where? At point D, right? So when you substitute Z is equal to 4, you have minus 40 times 10 to the power 3 multiplied by 4 plus by 160 times 10 to the power 3. The whole thing is equal to 0 and it's correct. This is how we check. Now, so now we have formed all our, so this is still minus 40 times 10 to the power 3. And then we have minus 40 times 10 to the power 3. Right, and then we have plus by 160 times 10 to the power 3. Okay. Z over here. Okay. So now when we have all these values now, okay, before I consider or go any further, I'm going to show you again if we do left to right analysis for this analysis C to D. Let's say we do again alternate, and I want you to see why is it important to learn both ways. Okay, alternate C to D and 3.2 Z to 4.0. Right, you will realize that there's a lot of terms to consider. Okay, so now we have this, right? Okay, so we know that over here is 120 times 10 to the power 3. So this is the easy part. Okay, so we know the distance from here to here is 0.8, and we know the distance up to here is our Z. So we know the distance from here to here, right, is Z minus 0.8. Okay, positive shear, positive bending moment. Okay, now the next point you have to be, the one on top, you have to be very, very careful. Okay, because it's in this range, right? Your so-called evenly distributed load now is a what? It's a constant, right? So now when that is a constant, that's where things get a bit what? Complicated. Okay, so you know that you over here is a constant, right? So you will have 50 times 10 to the power 3 multiply a distance of 2.4 plus 0.8, 3.2. So 50 power 3 times 3.2, 50 power 3 times 3.2 is equal to 160 times 10 to the power 3. And then we know that this distance from here to here is equal to what? So it's equal to 0.8 plus 2.4 divided by 2, 1.6. So the distance from here to here now, right? So distance from here to here now, right? So this distance is equal to Z minus 1.6. You can see here more components. Now, Y is easy, okay? So we do Y positive Y is equal to 0, right? So we can do 120 times 10 to the power 3 minus by 160 times 10 to the power 3. Oh, so sorry, V as a function of X should be coming down. Okay, positive shear, positive bending moment assumption. So minus V Z is equal to 0. So V Z is equal to minus 40 times 10 to the power 3. Okay, exactly the same. Then we look at the moment. Okay, so much more component now, right? So when we do the moment, right? Fortunately, we get all the distance right? So minus 120 times 10 to the power 3